Hello, and welcome to another installment of Geology 1 Processes and Products Lab DVD. My name is Renee Clary, and today we're going to talk about igneous rocks. Igneous rocks can form in one of two places. They can form on the outside of the earth, and they can form on the inside of the earth. If we look at our PowerPoint slide, here you see what happens when we have a rapid cooling. This takes place on the outside of the earth. This would be an extrusive igneous rocks, or a volcanic igneous rock. And notice that the texture would be fine grained. The crystals are smaller. Inside the earth, however, the magma has longer to cool, and therefore the crystals have longer to assimilate and grow. So we would have larger crystals on the inside of the earth, and this would be known as a phaneritic texture. Let's review a little bit. When we have an extrusive igneous rock, this is commonly called a volcanic igneous rock. It formed above the surface, hence the term volcanic. Usually it has small crystals, or if it cooled very, very rapidly, it can be glassy. In other words, no crystals formed. It has an amorphous composition or a glassy texture. On the other hand, if the rock cooled intrusively, it is called a plutonic igneous rock, intrusive inside the earth. It forms below the surface, and these have large crystals because they have time to cool slowly. Let's look at some of the igneous rock textures of the igneous rocks that formed inside the earth. The first one is a phaneritic texture. I'll bring this one over here. Here we have a piece of a gabbro. This is an intrusive igneous rock, and you can actually see the crystals. Now, if I bring it to the side, this is how the rock would look if I harvested it out in the field. But since we use a lot of these gabbros and granites for building materials, here we see a nice polished surface, and you can make out some of the larger crystals. This is known as a phaneritic texture. If you can see crystals like this in your rock set, then your sample must have cooled inside the earth. It's an intrusive igneous rock. Now, there are other examples of intrusive igneous rocks. Sometimes, I'm going to bring this big old slab over here, sometimes we have a texture described as pegmatitic. Here we have very large crystals. Just to give you a little scale here, here's a pen, and you can see that some of these crystals are bigger than 1 centimeter. If the crystals are bigger than 1 centimeter, we can describe that as pegmatitic. This texture, intrusive, and it also took a very long time to form. The crystals had a lot of time to assimilate. This is a pegmatitic texture. Let's compare that again to this guy. And you can see that the crystals of our gabbro are smaller when we compare to some of these big feldspar crystals in our pegmatitic rock. Again, both of these are intrusive igneous textures. Now, naturally, things aren't always easy in nature, so we have a texture known as porphyritic. In this texture, we have larger crystals mixed in with a smaller ground mass, the smaller crystals of the ground mass. And here's an example right here. This is a porphyritic texture. You can notice some larger crystals here and here. And the background, the ground mass, is finely crystalline. One way that this can form is that these larger crystals form inside the magma, inside the earth, and then as the magma moves closer to the surface of the earth, we end up with crystallization of the finer ground mass. So the background didn't have as long to cool, and therefore the crystal size is a little bit smaller, actually a lot smaller. When you have these larger crystals like this, these are known as the phenocrysts, And the black stuff, the background, is known as the ground mass. The phenocrysts are the larger crystals, and the smaller crystals are part of the ground mass. This is a porphyritic texture, usually associated at least partly with an intrusive igneous rock. Now, why are we going over these textures? Well, remember that we classify all rocks based on texture and composition. With the intrusive igneous rocks, we will have a crystalline texture. Remember, our textures can come in 3 different varieties, more or less. We can have crystalline, we can have a detrital or clastic, and we can have glassy. If the igneous rock cooled inside the earth, the intrusive igneous rock will have a crystalline texture. And the crystalline textures we have described are phaneritic, pegmatitic, when we have large crystals greater than 1 centimeter, and porphyritic, and this would be 2 sizes of crystals. The slide also shows you another example of a pegmatite or a pegmatitic texture. You can see the larger crystals. Unfortunately, this photograph did not include a scale, but these crystals would have to be greater than 1 centimeter across in order to qualify as a pegmatitic texture. Here's a photograph from Dartmoor, England, and this is a porphyritic texture. Here is a pound coin for scale. It's a little bit smaller than our quarter, our U.S. quarter. Here we have the larger crystals, the phenocrysts, and the smaller crystals, all of this kind of grayish stuff, is the ground mass. Now let's talk about extrusive igneous rocks for a while. Extrusive igneous rocks cooled on the outside of the earth, and therefore they cooled very rapidly. Extrusive igneous rocks can also be crystalline, but because the crystals did not have a long time to grow, the crystals tend to be fairly small. Usually you need a hand lens to see them. You can't see them with your naked eye. This is a sample of basalt. It is the most common extrusive igneous rock. The holes were formed from escaping gases, so it also has a texture known as vesicular. Vesicular because of the escaping gases, leaving this bubbly texture. But you might be able to pick out a few crystals here, but it's difficult. This would be an aphanitic texture. It cooled on the outside of the earth as opposed to the phaneritic texture, which cooled on the inside of the earth. Let's put these two together real quick. And I think you can see the difference. If you don't look at the holes in the basalt, but you try to look at the crystal size versus the crystal size here in the gabbro, you can see that the gabbro has some fairly large crystals when you compare to the basalt. Aphanitic texture. Okay, we also have a couple of other choices for texture for extrusive igneous rocks. As mentioned before, sometimes the igneous rock cools on the surface so rapidly that no crystals have time to form. In that case, we have a glassy texture or a hyaline texture. Then we get a volcanic rock, in that case, known as obsidian. This is snowflake obsidian. But you can see that it actually looks like broken glass, and that's what it is. It is glass, volcanic glass. Now, would this be classified as a mineral? No. Why not? Because we mentioned when we discussed mineral characteristics that a mineral must be solid. Not solid. It must be inorganic. It's inorganic. But it must be crystalline. This is not crystalline. A hyaline texture or a glassy texture means that no crystals formed, and therefore it would not be classified as a mineral, although it is, in fact, a rock. This is obsidian. Now, we can also have glassy textures or hyaline textures where we have a vesicular texture as well. And this little guy is a scoria. Think of lava rocks that we can landscape with. You can see all the little bubbles. You can't pick out crystals here because, again, it cooled much too rapidly for crystals to form. Now, sometimes a vesicular texture can even be frothy. And I'm going to pull this little guy in. This is pumice. It's very, very light, so light in fact that pumice is the rock that floats, and that's because of all the void space. It cooled very rapidly as the gases escaped. Remember, it's an extrusive rock, and it's also glassy because there are no crystals. Let me grab a beaker of water, and we're going to demonstrate quickly. I'll put it here. How's that? Here's the pumice, and it does in fact float. So these are all hyaline or glassy textures of extrusive igneous rocks. Okay, we've mentioned that we can have crystalline textures for extrusive igneous rocks. We can have a glassy or hyaline texture. We can also have a detrital or clastic texture, and that's when we have pieces coming together. When a volcano erupts and we get pyroclastic materials such as ash, when that is welded together over time, we can have a pyroclastic tuff. And I have a sample right here. There we go. Okay, this is composed of pyroclastic material, the solids erupted from a volcano that have been welded together over time. This is an example of tuff, T-U-F-F. Okay, let's review a bit. If we have an intrusive igneous texture, it has to be crystalline. It has to have a texture that's crystalline, but we can have different varieties. We can have a phaneritic texture. We can have a pegmatitic texture when the crystals are larger than 1 centimeter. We can have a porphyritic texture when we have two obvious different crystal sizes. If the rock erupted extrusively, let's go to the PowerPoint slide quickly, we can see that we have 3 different types of textures. We can have a crystalline texture. Whoops, there we go. Crystalline texture where we have small crystals, that's aphanitic. We can have a glassy or hyaline texture, that's when no crystals form. Again, these are not minerals, they are not crystalline. If escaping gases left a frothy or bubbly texture, we call that vesicular. And extrusive igneous rocks can also have a clastic, a pyroclastic texture. We can get tuffs or volcanic breccias. This is a picture of a piece of obsidian, and you can see that glassy fracture, the conchoidal fracture, looks like the quartz fracture. Here is a piece of a volcanic extrusive glassy rock. Again, it has no crystals. This would be a scoria. Here is a photograph of the tuff. These are all pyroclastic pieces that have been welded together. So it has a clastic texture. These aren't crystals, not individual crystals. They are pieces of volcanic solids that have been erupted. Okay, and there are usually diagrams available that will help you to identify what you might have. Notice on this side of this diagram, we're looking at mineral composition, and on the other side, we're looking at textures. Why is that? Well, remember, we classify all rocks based on texture and composition. We've just covered the texture, so let's look a bit at the composition. There are many different words that can be used to describe the composition of igneous rocks, but the most basic are felsic. This is when we have light-colored minerals, quartz and potassium feldspar. Felsic rocks are more indicative of crustal rocks. Mafic rocks are our darker minerals. They are also more dense. They're heavier. We have plagioclase and pyroxene. These rocks are indicative of the mantle. Finally, we can have an ultramafic rock. The ultramafic rock would form deep in the mantle. Olivines and pyroxenes. Now, N.L. Bowen described the order of crystallization, and his famous Bowen's reaction series is a must for igneous rocks. You've probably seen this diagram in several different versions. Note that on the left side of the diagram, we have order of crystallization in a discontinuous series. In other words, as the magma cools, we see the formation of olivine. Olivine crystals come out of the melt. Then the olivine crystals will start to react with the melt, and we will start forming pyroxenes. Pyroxenes will react with the melt, and now we'll form amphiboles, and then the next step would be biotite micas. If you've read anything about the different types of silicates, you know that Bowen's reaction series will also mimic the different structures of the silicate minerals. In other words, 3D structures, and then we have chains, double chains, and sheets. On the right side of the diagram, we have a continuous series. This is the plagioclase feldspar series, but we move from calcium-rich at very high temperatures all the way down to sodium-rich toward the bottom. Now, there's something really important to keep in mind with Bowen's. This is an idealized diagram. In other words, once we get to lower temperatures and we start forming potassium feldspar, muscovite mica, and finally quartz, idealized, it will only happen if we have enough silica in the melt. Sometimes we never get to these rocks. It depends on the composition of the melt and what the silica content is. Let's think about this for just a minute. Let's say that we have an assemblage of rocks: olivine, pyroxene, amphibole, biotite, and quartz. What would happen if we had a container that would withstand a lot of heat and pressure, and we took these rocks and pressurized them and heated them up? Which rock would melt first? The olivine, the pyroxene, the amphibole, biotite, quartz. What would melt first? Well, remember, we crystallize out in this order. So as the melt gets cooler, we see the olivine come out first and the quartz come out last. So if we reverse the situation and have a rock and start melting, we end up with the quartz melting first. This is a diagram that is a fairly easy way to classify both extrusive and intrusive igneous rocks based on a very generalized composition. Note that we have volcanic at the top. These are the aphanitic textures. We're going to stick with just the crystalline rocks this time. The intrusive igneous rocks have the phaneritic texture. Again, we see the crystals only barely here. We need a hand lens to see the aphanitic texture. With an intrusive igneous rock, we can see the crystals right away. This has a phaneritic texture. If we look at a very basic composition, felsic, meaning the light minerals, mafic, meaning the dark minerals, and then we'll kind of cheat and say intermediate between felsic and mafic, we will end up with different types of rocks based on texture. Here is our composition: felsic, mafic, intermediate, and our texture would be either aphanitic for extrusive or phaneritic for intrusive. Now over here in this column, I've also added some ultramafic igneous rocks. Komatiites, which formed extrusively an ultramafic lava flow, are not common anymore. They are indicative of the Archean eon, way, way, way long ago, when we knew we had a hotter Earth back then. We occasionally find periddotites for intrusive ultramafic rocks, and these are indicative of the deeper mantle. Let's look at some of these rocks. Let's keep in mind, though, that felsic compositions can give us either rhyolite or granite, depending on whether the magma or lava cooled extrusively or intrusively. If we have an intermediate composition and it cooled inside the Earth, we'll have a diorite. Outside the Earth, we'll have an andesite. And finally, if we have a mafic composition magma cooling inside the Earth, we'll have a gabbro. And cooling outside the Earth, the lava would produce a basalt. The most common intrusive igneous rock is granite. The most common extrusive igneous rock is basalt. Let's look at some of these. In the photograph, we see rhyolite on the top and granite on the bottom. Let's move to my rock samples. Oops. There we go. Now, this hand sample, we can see the crystals. Nice large crystals. You don't need a hand lens for that. This would be intrusive. You can tell right away because you can see the crystal size. Here we have some fairly small crystals. The composition is basically the same, or as close as I could get in two hand samples. This is an extrusive, this is an intrusive. Granite versus rhyolite. Now here are some photos of some intermediate composition igneous rocks. Note that the one on the bottom, we can see the crystals. This is diorite. I commonly refer to this as the salt and pepper rock. It looks to me just like grains of salt and pepper, a little bit larger stuck together. The extrusive version, if the magma had actually made it to the surface to cool, would be andesite, an intermediate extrusive igneous rock. And I do have some hand samples of that as well. There we go. Okay, so which one cooled on the inside of the earth? This one, right? You can see the crystals, our salt and pepper diorite, intrusive igneous rock. The texture would be phaneritic. It is a crystalline phaneritic texture. This, on the other hand, because the crystals are very, very tiny, you can pick out a few that are kind of shining in the light. This would form extrusively on the outside of the earth. Again, it is crystalline. There are crystals here. It would be aphanitic. But both of these are intermediate composition. This one formed intrusively, this one formed extrusively. Composition is similar. The texture, the crystal size, is different. Let's look at the examples of a mafic composition. If we look at the top photograph, this is basalt. However, if that magma had cooled inside the earth, we would end up with a gabbro. Gabbro, again, would have large crystals. And I do have some examples of that as well. Okay. Okay, we have, whoops, let me move this guy around so we can maybe see some of his little, there we go. Here we have nice large crystals, and on this side we have crystals that are smaller. Which one cooled inside the earth? This guy, right? Because we have larger crystals. This would be a phaneritic texture. In this case, we have a dark magma, a mafic magma, that made it to the surface of the earth. We would now call it lava, and it cooled extrusively. There are crystals here, but they're very tiny. This would be an extrusive crystalline rock, an igneous rock. This would be aphanitic versus phaneritic. Again, same composition of magma, and that's why we identify rocks based on texture and composition. Composition-wise, these are pretty much the same. Texture-wise, they're not. This one cooled inside the earth, this one cooled outside the earth. This is a slide of a peridotite, an ultramafic igneous rock. And unfortunately, I don't have a hand sample of that. And here is a photo taken out in the field. These nice green nodules are peridotite. These are xenoliths. These crystals formed in the magma inside the earth, but these pieces of mantle were basically carried up in the basalt as it erupted. So these crystals, these peridotite crystals, formed inside the earth, and these xenoliths, as they're referred to, were carried up when the lava erupted on the surface as basalt. Now, let's review. What are these holes indicative of? What does that mean? Is that weathering? No. This is a vesicular texture, and this is formed by escaping gases as the basalt quickly cooled. Okay, let's review just a little bit. Remember, when we're identifying rocks, we always look at the texture and the composition. We first want to determine whether or not the texture is intrusive or extrusive. If we have large crystals and we can see the crystals, we're looking at an intrusive formation. If we have small crystals that we can only see with a hand lens, we're looking at an extrusive formation. Now, extrusive rocks, igneous rocks, can also be glassy, and this is when the lava does not have enough time to organize itself into a crystalline texture. Instead, we get a glassy or hyaline texture. And again, these aren't minerals. They have to be crystalline in order to be minerals. And our last type of extrusive igneous texture would be that of a pyroclastic texture, when the pyroclastic materials such as ash came together, welded together over time. So the first thing we do to identify an igneous rock, if we have several of them, let's look at them and determine intrusive versus extrusive. Large crystals only, or glassy texture, small crystals, or even a pyroclastic, which you'll probably run into less commonly. After that, we're going to estimate the chemical composition of the rock. Remember the diagram, move from felsic, intermediate, to mafic, and then whether or not you can see the crystals, and you should be able to fairly easily identify what type of igneous rock you have. The last thing we're going to talk about in this segment on intrusive and extrusive igneous rocks are intrusive igneous bodies, commonly referred to as plutons. Remember when we first mentioned that extrusive igneous rocks are called volcanic rocks and intrusive igneous rocks are called plutonic rocks? Well, now we're going to talk about those intrusive igneous bodies known as plutons. Here we see that, let's see if I can get my pointer, there we go. We have basically two different types of plutons. Those that are emplaced parallel to the existing country rock are called concordant, and those that cut across the existing country rock are referred to as discordant. Concordant, or the parallel structures, can be in the form of sills, or if they're lens-shaped, and I'll show you an example of that on the next slide, they're referred to as laccoliths. The discordant igneous bodies, the ones that cut across the country rock, can be simple dikes, or if we're looking at a volcanic structure, that original structure that connected the crater to the magma chamber down below is referred to as a pipe. If over time the volcano no longer erupted and much of its exterior was eroded, leaving behind only the resistant part of the igneous rock that connected that crater to the magma, it's now referred to as a volcanic neck. This is the erosional remnant of the pipe. We can also have large discordant igneous bodies. We can have stocks. These are large, but we still have a larger variety. Stocks are less than 100 cubic kilometers in volume. However, if we have very large intrusive igneous bodies, these are referred to as batholiths. The next slide will give you a little bit of visualization on how these plutons fit into a landscape. Okay, in this diagram we see an active situation where we have the emplacement of these intrusive igneous structures. Here we have a big magma chamber down below, and magma rises up and cuts through the country rock. This, of course, would be discordant because it would be cutting across the existing rock. Now, these nice parallel areas where the magma is emplaced are referred to as the concordant structures. And here we have a larger concordant structure. It's in a lens shape, and guess what? That will become our future laccolith. Here we have a little erupting volcano up at the top. Now, over time, we're going to have the cessation of this igneous activity, and this igneous rock will have slowly cooled, and we'll end up with some of these intrusive igneous structures. These that cut across will be the dikes. These little parallel structures will be sills, and this nice lens-shaped concordant structure is a laccolith. Now, down below we have a lot of igneous rock, and eventually that's going to be exposed at the surface. Note our volcano up here. A lot of its exterior has been eroded away, and what's left is that pipe that used to connect the crater with the magma chamber way down below. This is a volcanic neck. the erosional remnant of a pipe. Okay, now let's suppose our landscape experienced a lot of uplift and erosion. All of these structures and sediments and layers are gone. Instead, what's exposed down here are the original igneous rocks that were part of that magma chamber. The smaller one, that is 100 cubic kilometers or less, would be called a stock, and this huge igneous intrusive body that was once deep inside the earth is referred to as a batholith. I do have a slide to show you a couple of field diagrams, pictures of Shiprock, New Mexico. This is a famous volcanic neck, the erosional remnant of a pipe, and this is actually an exposed dike on the surface. Remember, it's an intrusive igneous body. It once cooled inside the earth, but with subsequent erosion and uplift, it's now exposed. That will conclude this segment on intrusive and extrusive igneous rocks, as well as intrusive igneous bodies. If you have any questions, please feel free to contact your instructor. He or she will be very happy to assist you. Thank you for joining me today, and have a good day.